hopefully. Can you hear me from remote?
Yes.
Perfect. So, we just repeat the small exercise that we made during the last lecture to be clear and to explain a bit more. During the last lecture, we addressed the concept of phase delay and say optical path. And we said, okay, if I have a flat plane wave, and if this flat plane wave is accessing a region in which I have two materials with two different refractive indices, and I said at a certain point, this flat wave will reach the interface between the two materials and it will enter inside the materials. And say that we take an x-axis like this, that we put the origin here. This is the thickness of the two media, D. And then we ask ourselves, if we take a look at this plane here, how are they the fields when they reach that flat part here? The field here will be given, say we call it E1, will be given that by an amplitude sinus K1 D minus omega t. Okay? So, who is K1? K1 is the wave number inside the first medium, and you remember K1 can be written as K naught, that is the wave number in vacuum. This is the wave number that the wave has got in vacuum times the refractive index N1. And I remind you that K naught is 2 pi over the wavelength in vacuum. Okay? If you look at this point at the same time t, the electric field will be given by E naught if we think that the amplitudes of these two waves are the same because they originate from the same plane wave where the amplitude is the same everywhere. This is a sinus K2 D minus omega t. So it means that the two fields are like that. Okay. Then I ask myself, what is the phase difference? This is the phase of the first field. This is the phase of the second field. What is the phase difference phi 1 minus phi 2? This is, of course, the difference of these two expressions. The time is ruled out. So you have a K1 minus K2 times the thickness. Okay? And this can be written like K naught N1 minus N2 times the thickness of your sample. Okay? So if the two materials are the same material, N1 equal to N2, this difference is 0. There is no phase difference. What does it mean that there is no phase difference? That this is a flat wavefront. The field is the same here and here. Okay? If the two refractive indices are not the same. The phase here and the phase here are different, and the field is not the same in the two regions. There is a difference. Now, this expression here can be written in a different way by using the concept of optical path. You remember that if I have 2 points in the space which are at a distance d, a geometrical distance calculated with the laws of geometry that we know, I can define an optical distance as the geometrical distance times the refractive index of the medium in which I am propagating. If I do this, this can be written like K naught times L optical 1 minus L optical 2. Okay? What is the meaning of this expression? The meaning is that it is as if I am propagating in vacuum with K naught, but with a distance that is not the geometrical distance, but is the so-called optical path. So the things go similarly to what you would have in vacuum, but if you would travel along a longer distance. Okay? And the phase difference is the difference of the two optical paths times the K vector in vacuum. Of course, this can be, you can think in terms of this and this, of course, or you can think in terms of optical path. Okay? Jesus. Yes, I am. Right. Okay. So this is the expression that I. What does it mean? It means that, as a matter of fact, when the wavefront is coming out from this medium, the wavefront is split in two parts. Okay? So all over these two parts, the field has got the same value, but you need to travel more here to get to the same phase. So there is a phase difference. Okay? Now one can, in an exercise, in a problem that you could find in your test, one could ask you, okay, what is given N1, N2, and the wavelength. So if you know the refractive indices and the wavelength of light, given these values, what is the thickness such that the phase difference is pi? Say, I could ask you a question like this. No problem, because you use this formula here. K naught, you know, because it's 2 pi over lambda naught. You know the difference of the refractive indices. You can equate this expression to pi, and you can work out d. Or in a problem, I could ask you, okay, what must be the refractive index difference if you have a material that is 1 millimeter thick and you want a phase shift of pi over 4? Of course, you can calculate this. Okay? That it's clear? Now, we are not here in a photonics technology course, but this is exactly the way it works, an electro-optic modulator in optical communications. In optical communication technology, you can fabricate an optical waveguide something like this on top of a wafer, So a waveguide is a device in which you can inject light in one extremum of this system, and you can detect light here. If you fabricate this waveguide and you make it perfectly symmetric, what does it mean? It means that the two arms, the arm number 1 and the arm number 2, are exactly the same. Then what does it happen? That light is injected here. It is split in 2 equal parts here. These 2 equal parts recombinate here. And since the path is exactly the same and the waveguide is made of the same material, they get here in phase. Okay? So what does it mean that they get in phase? That they sum up coherently. Okay? And you have intensity here. But if you fabricated your waveguide with an electro-optic material, for example, lithium niobate, and you apply an electric field here, by applying an electric field, a static E field, you can change the refractive index in this region. Then what does it happen if you change the refractive index here? You unbalance this device. You can introduce a phase difference. And if the electric field is such that the phase difference here is pi, when they recombine the two fields, they are in phase opposition, and they sum up to 0, and you get 0 here. Okay? And this is an electro-optic modulator. This is this device that is actually used in the telecom systems. Okay? Here, the wavelength lambda naught is 1.55 microns. That is the telecom wavelength. The material is lithium niobate, and you exploit this phenomenon to modulate light. So you can switch on and off the light that comes out, and you can make bits 0, 1, 0, 1, 0, 1, 0, 1. And you can make it at a very high frequency, up to 100 gigahertz. Therefore, you can increase the transmission rate on the channel. Okay, this is just an example. Now, what does it happen? What does it happen if you have a slab of material N1, N2, N3, N4, N1, N5, N3, and so on. A slab of material with many different values of the refractive index. Then you have a flat wavefront that is getting inside your material, and the refractive index difference is imprinted in your flat form. So you will have at the exit something like, say, I am going in a very magnific way, yeah? And so on. You transfer the information that you get here on the way, okay? And in particular, you can synthesize any wavefront you wish by using your material. If instead of a material that is made out of glasses, several different types of glasses, you use, for example, what is inside this projector, a liquid crystal phase shifter, you can make it dynamically, and you can change dynamically the wavefront as you wish. If you have attended the seminar from Professor Capasso during the conference EOSAM 3 weeks ago here in this faculty at Harvard University, they exactly do this. Okay, they call them metamaterials, and to do that they use very tiny gold structures on top of glass to modulate the refractive index. Okay, And this is just to point out, to resume what we said during the last lecture. Okay? Now, during the last lecture, we introduced the Snell law, you remember? And we said, look, if I have an electromagnetic wave that is impinging at an angle I on the interface between two media, and say, for example, that N2 is larger than 1, we understood that there are differences, then this light will be partially transmitted inside the second medium and partially reflected in the same medium. So you have reflectance and transmittance. Okay? We gave a law that is relating the angles, the incidence and the transmitted angle, and this is the so-called Snell law. Okay? We understood that depending on the relative value of the two indices, the light that is coming at a certain angle can go towards the normal or far from the normal. Okay? And we understood that if I am in a condition in which I am coming from a high index material to a low index material, then there is one particular angle that is named total internal reflection angle, and at this angle the refracted light comes back at this angle. So the transmitted angle is 90 degrees, and this is the reflected angle. Okay, this particular angle is called the total internal reflection, or limit angle or critical angle. Okay, and we understood that sinus of this angle divided by sinus pi over 2 must be equal to N2, N1 divided by N2. Okay, this term here is 1, okay, and therefore this critical angle is arc sinus N1 divided by N2. Why is this very important for us? Because this is the base of the total internal reflection microscopy. That is one type of microscopy that we shall discuss. Okay? But when we gave this law, this is a geometrical law. It doesn't.
Sorry, Professor. The video is stopped. The video is stopped.
Please, can you repeat?
Video is stopped. I can't see what you
Video is stopped.
Yes.
Just now. It is just now.
Yes.
Okay. Let me. I restart the camera. Let's restart the camera. Does it? Yes, it does. Just a while and it restarts. Camera control. Okay, here we are. Can you see? Yes?
Yes, it's okay. Thank you.
This is a geometrical law. There is no information about the relation between the incident, say, average intensity, the transmitted average intensity, and the reflected average intensity in this law. Now, information concerning the relative intensities, so how much light is it transmitted and how much light is reflected, is given by the so-called Fresnel laws. Okay? Now, what are the Fresnel laws? Or rather than Fresnel laws, these are named Fresnel equations. What are the Fresnel equations? And we must be a bit more how to say, precise with Fresnel, and say we have an interface. This is the normal to the interface. We have two media, say N1 above and N2 below. And we ask ourselves, okay, can I relate the intensities or the amplitudes of the fields that are incident, reflected, and transmitted? And I ask myself, may I find an expression for the so-called field reflection coefficient, that is the ratio between the electric field that is associated to reflected wave divided the electric field that is associated to the incident wave. Okay? So the Fresnel equations are concerning the reflection phenomenon. Okay, so we address this reflection phenomenon. And I ask myself, how much is this ratio? If this ratio is 1, it means that the incident field is completely reflected back, and so on. Be careful when in your future life that this is a complex number. That means that the reflected field can have a different amplitude and a different phase with respect to the incidence field. There can be a change of the amplitude and a change of the phase. Okay? Now, we shall see that the reflection coefficient given by the Fresnel formula depends on the polarization of the incident light. In Snell laws, here, we didn't tell anything about polarization. We didn't speak about the polarization of this incident beam because the Snell law is valid for any polarization of the input light because this is a geometrical law. Okay? But in Fresnel, there is a difference. And now, what did we say speaking about polarization? We said, oh, look, in a plane wave, light is propagating in a direction that is perpendicular to the plane. You remember this? Okay? And we said, oh, look, the field must be in the plane, but it can have any orientation. And then we said, okay, it means that the field may have two components, y and z. Okay? And we wrote, okay, you remember the electric field has got two components, one that is A, Y, and one along A, Z, and we discussed all the cases. Okay? Now, the choice of these two axes is completely arbitrary. As an engineer, I can decide, okay, I rotate the y-axis, y prime, and I take an x-axis like this. It would be the same. But nevertheless, to describe the field, I'm using two components here. Okay? Now, so to describe polarization of light, you need two components. Now, when you study reflectance, and of course, I didn't tell it, but we are thinking that these are plane waves. I am speaking about plane waves. When you are describing reflectance, the choice of these two directions that you use is not really free. Why it is not free? Because you see here that there is a natural direction for this system. As soon as you have an interface, and as soon as you have the normal to this interface, this is fixing a direction. Okay, so the interface somehow is a reference for you. So it is natural that if you want to describe the polarization of the field, the two directions that you use as reference direction are the direction in the plane. So one axis, say the y-axis is in the plane. Oh, sorry, here I should have written Z1. Okay. One direction is this direction, and the other direction is the direction perpendicular to the plane. It is natural to describe the polarization using these two directions, okay? Because it's clear that the interface and the normal are making that there is a preferential plane. And what is the preferential plane? Is the plane of the blackboard or the whiteboard here. By the way, this plane is named the incidence plane. That is the plane that is containing the incidence direction, the reflected direction, and the refracted direction. Okay? Now, this direction here is named the P direction in plane, in the plane. And this direction here is named in optics the S direction. So you can have two polarization of light, linearly polarized along P, linearly polarized along S. Okay? If you have a field that has a certain angle, you will have to deconvolve it on the two directions, P and S. If you have a field that is elliptically polarized, you will have to deconvolve on the P and S direction. So the two preferred directions in this case are fixed. Now, generally, this P polarization you can find in textbooks that is referred to as pi polarization. You can find this. And this S polarization is also given by the Greek sigma letter. Okay, sigma polarization. Many people in electromagnetics, okay, also use the definition to say that this is the transverse magnetic polarization and that this is the transverse electric polarization. But a purist in optics, so a man who is very strict about definitions would say that these are improper as, you know, how to say, symbols. Because these symbols are proper only in waveguiding system, in confined modes. What does it mean, transverse electric? If the field is polarized S, it means that the field is like this. So when it gets here, the field is transverse with respect to the interface, is along the interface. If the field is p-polarized, the electric field, then the magnetic field is like this, and the magnetic field is transverse. So this is transverse magnetic, transverse electric. So you can find all of these notations on the books, and we can use one or the other. That's the same for us. Okay. Now, what do we find out? And we don't demonstrate this. We find out that if you are using light that is S polarized, okay, then this reflection coefficient is given by this expression here. Is given by this expression. So in the case that you have light that is linearly polarized along S, then the reflection coefficient is given by this expression here. If you have light that is polarized along the P or pi direction, then you get that this reflection coefficient has a similar structure, but instead of the sinus, there is the trigonometric tangent function. So these are the two field reflection coefficients for your interface. Okay? But we are interested in, at least in this course, in optics, we are interested very much in that. But in this course, we are interested not to how much field is reflected, but how much intensity of the light is reflected. And remember that we said that the intensity, or say that is proportional to the square of the field. Okay? Remember this. Therefore, if I define an intensity reflection coefficient that is the average intensity of the reflected light divided the average intensity of the incidence light, since both intensities are proportional to the field, you will see that this is given by this expression. And so this R coefficient, as a matter of fact, is the square modulus. These are moduli. Oh, let's write this. These are, sorry, moduli. Okay. This is the square modulus of R. And so this reflection coefficient is a real number. Okay. And this gives you how much intensity is reflected and how much intensity is transmitted is in the two polarizations. Now, if we take these two expressions, that means that the RS coefficient is sin squared theta I. Sorry, I called it theta, no? But as a matter of fact, this was I, this was T, I plus T, and so on, also in this expression. So I can write here I minus T sinus square I plus T, and the RP or pi, let's say RP is tangent squared divided by tangent squared minus I plus T. These are the two intensity reflection coefficients. Okay? Now, of course, always remember that I and T are related by the Snell law. So if you know the refractive indices for a given I, you know the transmitted angle, then you can calculate this difference and this sum, and you can calculate the reflection coefficient. Okay? So if N1 and N2 are given, if I is given, you can calculate R along both polarization, S and P. Okay? Now, how do they look like, these two curves? If I plot the reflectivity as a function of the incidence angle. So if I ask myself, okay, think we have an interface between two media, N1 and N2, okay? And let's assume that the refractive index of the second medium is larger than the refractive index of the first medium. So, for example, you have light coming from the sun, and it is entering inside the glass of the window. Then you ask yourself, for a given angle I, how much light will be reflected? And if I change this angle, how does it change the reflection coefficient? Then you want to plot the R coefficient as a function of the incidence angle. The incidence angle can be in between 0 and 90 degrees. You can change it between 0 and 90 degrees. Then these two curves appear like this. If this value is 1, so reflectance equal to 1, these two curves appear like this. They start from the same point A, they get here to the same value B. This is the curve for the sigma polarization, and this is the curve for the pi polarization. So what does it mean? It means that if you have light that is sigma polarized, okay, like this, if you start from 0 incidence angle, you get a reflectance that is different from 0. Some light is reflected back. If you increase the angle, the surface reflects more and more and more. And when you get 90 degrees, the reflectance is 1. All light is reflected. Okay? But if you have light that is p-polarized and you start from 0 incidence angle, you start from the same value, but instead of increasing the reflectivity decreases up to a certain point where it gets 0, and then it grows again and goes here. This particular angle here is named I. Brewster, from the name of the physicist Brewster. Sorry, there is an S missing. From the physicist who studied this. And we shall now show you how much it is this angle. Okay? Be careful. This graph here relates to this condition where N2 is larger than N1. Okay? How would it appear, this graph, if you would be in such a condition? If you have n1 and n2 less than n1. How would it be, this graph? It would appear like this. This is the incidence angle. This is 90 degrees. This is the reflectance. This is the box where this is 1. Now you know that in this case, it exists a total internal reflection angle. Well, what is the meaning? It means that if you reach the total internal reflection angle, what does it happen? Light is completely reflected. So if I mark here this total internal reflection angle, reflectance above this angle must be 1. Light is completely reflected. And the two curves that you have seen before are some compressed in this region. So they look like this. They are similar, but they are compressed in this region. And this is the Brewster angle here, and this is 0. Okay? It's clear this. So depending on where you are arriving from, you can have this graph or that graph here. Okay? Now, how much is the value of this Brewster angle? Okay? And the value of this Brewster angle comes, this is the Govern, my pen is finishing, I write in red. My RP coefficient is tangent square I minus t, tangent square I plus t. Now you see what does it happen. When I plus t is equal to pi over 2, so when the sum of these angles is pi over 2, the tangents gets to infinity, and this ratio gets to 0. So what is the condition for this angle? Is that the sum of these two angles must be pi over 2. And now look at what does it happen. It means that t is pi over 2 minus I. Okay? But you know that the two angles must be related by this formula, by the Snell law. But you know that under this particular condition, t is pi 2 minus I. But sinus pi 2 minus I is the cosinus of I. Okay, so the passage here is that you get sinus I divided sinus pi 2 minus I is equal to the ratio of the two refractive indices. That means that the tangent I must be to the ratio of the two refractive indices. Okay? So we call this Brewster angle, the angle at which we have such an effect. Okay? Is it clear? Then, if, for example, you have an interface between air, this is N1, and water, and this is N2, this is N2, and air has a refractive index N1 that is equal to 1, and water has a refractive index that is 1.33, then the tangent of this Brewster angle is the ratio 1.33 divided by 1, that is 1.33. Could you please calculate how much is this? This is I Brewster. This Brewster angle $53. is 53 degrees. So for an interface between air and water, this angle is about 53 degrees. Okay? And you could tell me, so what? And then what do I do with this? What do you do with that? That means in an example, in a classical example, where are you from? Iran. In a classical example, if you are in a developed country, so in a country in which culture is stable since at least 3,000 years, so here in Greece, in Iran, and in Iraq, and maybe a bit in China. In these countries, when you are at the sea, okay, you are on the shore of the sea, you are watching the sea, more or less during the day, the sun is sending light to an angle that is around 45 and 50 degrees, more or less. We told that light from the sun is not polarized. So what does it happen to this light when it gets to the surface of the sea? It is reflected by an interface between air and water. The reflection coefficient for the p polarization is almost 0 in this interval here. So the p polarization is not reflected, and therefore the light that is reflected is mainly as polarized. Is polarized. Okay? Of course, this is not perfectly polarized because some rays will get to a certain angle. And therefore, if you are at the seaside and you are annoyed by the reflection of the light on the surface of the sea, what do you wear? Polarized eyeglasses. And these polarized eyeglasses are made out of a material that transmits only light polarized like this. Okay? So the light that is coming from the sun that is polarized like this doesn't go through. And you just see the light coming from the other details that are not polarized. So you eliminate the reflection. But if you live in Iran, okay, and you are scared by airplanes, war airplanes coming from Qatar, from Arabia, Saudi Arabia, and so on, at the shore of the sea, basically what do you have? Is that you get radars, okay? To observe but we have in Italy, we have in the States, we have it everywhere. What do you need a radar? A radar is to see an airplane or a drone. You illuminate with electromagnetic radiation, you send electromagnetic radiation, and you want to get the echo back, and you measure the time. You measure with the altitude, you measure with rotation, so you can get position at a certain distance and the angles, the elevation and azimuth angles, okay? But if you are in a situation like this, the airplane will scatter back light in all directions. This light will also be reflected. This light travels for a longer path. So if you are using pulses to illuminate, you get a reflection after 1 second, but you also get a reflection after 1.5 seconds because light is, and this phenomenon is named clutter. And you don't know what is the distance of the airplane. You want to eliminate this clutter, but this clutter is polarized. Then you polarize your detector, or you illuminate with polarized light. That's why the radars are polarized. Okay? And you rule out this, and you know what is the distance. Okay? This is for war planes, but also for civil planes. It is important. So keep this in mind. So a simple interface between two materials can be used to polarize light. Okay, and in optics, the polarizers are made out of a piece of glass, basically, or several pieces of glass. Okay. Okay, so just let me resume before we stop for a while. So we gave Brewster. No, the last thing before we stop, so I don't forget it. This value, okay, is very simple to calculate. That is the reflectance at normal incidence, okay, is the same for the two polarizations. So the two values here are the same and are simply calculated like this. You simply can do to the power of 2. Okay? You simply calculate like the difference of the refractive indices of the two media divided by the sum, and you elevate to the square root, to the root of 2. Okay? Why should they be the same? Why are they the same? Because when you are at normal incidence, this is the normal to the plane, like this. This is the key vector of the wave that is coming like this. The incidence plane is not defined. What is the incidence plane here? Is the plane that is including both n and k. So this is the plane of the whiteboard. When k and n are along the same direction, the incident plane is not anymore defined. That means that for you, the P and S polarization are the same. There is a degeneracy. There is no meaning to speak about P and S polarization if you are at normal incidence. And these two values are like that. Now, just to give you figures, okay? If you have a glass air interface, so glass has a refractive index 1.5, air has a refractive index 1. What is the reflectance at angle 0? Is 1 minus 1.5 divided 1 plus 1.5 to the square of 2. So this is 0.5 divided by 2.5 square of 2. It is 1/5 to the square 2 is 1/25. And this is 0.04. 0.04 means 4%. So if you have a piece of glass and you have light coming from air and getting inside glass, at the interface, 4% of radiation goes back. So in that window there, in this room, sunlight is reflected at the entrance interface by 4%, then 96% is inside glass, and then there is a further reflection at the second interface. In the end, 7% of light goes back. Okay? You have this. But if you have a silicon air interface, a silicon wafer, and air, then silicon in the visible range has a refractive index of 3.5, more or less. Air has got 1, So this reflection coefficient is 2.5 divided by 4.5 to the power 2. And if you calculate this, .3. That means 30%. That's the why silicon looks metallic when you watch it. It reflects a lot. I am a monkey because we call ourselves humans, but we are more monkeys. We are closer to the monkey than to God. Surely, we are monkeys, and when we watch this, oh, it's a metal, because we are acquainted to a metal's reflected light. But if you are an engineer, then you have to ask a question yourself. What is the question that you have to ask? Look, I am an engineer. We are in the green transition. I want to use solar cells to get light from the sun. But if I fabricate a solar cell like this, and sunlight and normal incidence, and just by reflection, I lose 30%, I understand that I'm losing 30% of the energy of the sun. So I must do something here to do this here. I have to modify the surface to make that reflection is 0. And I can do it by simply putting my solar cell in an oven with water vapor. I oxidize the surface, I grow a tiny layer of silicon dioxide on top, and this tiny layer behaves as an anti-reflective coating. And you get no reflection. Now, in the second experiment you will make, there will be the possibility to measure that. So you will see that, okay? This formula can be useful for the tests, okay? The Fresnel formulas can be useful for the test that you have to pass in some week, okay? So we stop here for 10 minutes and then we start again. So it's 10:04, at 10:15 we start again.